All right, so this is our final review. We have a little electrochem, little gases, some intermolecular forces, all sorts of thermodynamics. I don't have a lot of equilibrium, but equilibrium kind of filters in here. But we focus on more equilibrium during some other reviews as well. Okay, so that's kind of where we're heading here. So we are going to jump right into it. We're getting on our first problem. You guys are ready? So we have a cell right here, and it looks very different. And this is the one in 2015 that blew students' minds because they didn't know what they were looking at all. So what you need to understand is every cell has two compartments usually. It has something on the top, either a battery or voltmeter, and you have to have a salt bridge at some point. Either a porous plug, that thing that's actually literally like a U-tube that's a salt bridge, or in this case, it's electrolyte paste. So, metal air cells are a relatively new type of portable energy source consisting of a metal anode and an alkaline electrolyte paste that contains water in a porous cathode membrane that lets in oxygen from the air. Schematic of the cell is shown above. The reduction potentials of the cathode and three possible metal anodes are given in the table below. All right, so to give you all of it again, you don't have to be looking it up. You know that you have it. And don't let the picture confuse you. They even tell you where the electrons are flowing, which is a big help as we go. And A, early forms of the metal air cells use zinc as the anode. Zinc oxide is produced as the cell operates according to the overall equation below. So they give me the equation. So we have an AI and an A double I. Whoa. All right, so it says use the data in the table above, calculate the cell potential of the zinc air cell. So as always, you're given an equation. You need to figure out what the potential is based on all the other equations that you're given. So you got to use the information from the balance equation to what you may think you have up there. And then if you can try to move ahead, I'll let you, you can definitely go for it. It says the electrolyte paste contains OH minus on the diagram. The cell above, draw an arrow to indicate the direction of the migration of the OH minus ions through the electrolyte as cell operates. But try to figure out what equations, two of them, that you're using, and because of that, what is the cell potential? So I will say one hint on this. I see a voltmeter. Wow. See a voltmeter, so that means my voltage has to be positive. Okay, that's my first goal. Okay, so give it a shot, see what you can come up with. See if you can get the proper voltage. Which ones are you going to grab to make the equation reflect the one that they already gave us? See if you can figure it out. Honestly, one big hint I do is I like to underline the products and the reactants, and then I like to try to find them in the equation. And if equations don't really have those, then I'm not looking at those. Okay. For the second part, which way is the OH minus going to go? What have we been learning about cells? The salt bridge, or whatever that would be, it compensates for the loss or the gain of negative ion or electrons or the charge, and it helps balance it out. So if you're looking to say where the OH minus ions are going to go, that means it needs to go in the direction where that cell is losing electrons. Right? Does that make sense? Because I'm losing electrons, I need to get that negativity back in that cell, on that side. Anybody get a voltage they feel good about? Sophia, what did you get? That is the correct answer. Good find. So it's these two, right? It's got to be this one. And then, assuming that this has to be flipped, I would have had to flip this one to get to the 1.65. Good. Because there's my, here's my zinc, right? There is my oxygen, and here's my zinc oxide. So those are the atoms that I was looking for. So very good. So to show your work, so you got to show something. I would have shown this. And get my answer. Okay, so let's take a look at my picture here. Which way should the OH, so OH is literally sitting in here. That's what it's telling me. So which way should it go? Should it go that way, to the left, or should it go to the right? Okay, to the left, because it says that the electrons are flowing this way. I think they did this on purpose where they wrote electrons only here, but electrons are also, that means it's flowing like that. And that's what that means. So I would need my negative ions in my salt bridge to compensate for that loss. Good. And that was one more point right there. So that's a good start. Here we go. Now it doesn't totally reset, but it asks some different kinds of questions. A fresh zinc air cell is weighed on an analytical balance before being placed in a hearing aid for use. I, as the cell operates, does the mass of the cell increase, decrease, or remain the same? In anything I do in chemistry, if it talks about as something is continuing on, as a reaction is going on, and they give me a balanced chemical equation, it is always at least the first instinct that I have to look at. Okay, so think about this. As the reaction continues, is the battery getting heavier? That's all it's saying. So first you have to answer that, and then you have to justify. So give it a shot. Think about what you're actually seeing. And I have given you a hint. It is about the chemical equation. The mass of the battery is basically zinc. And as it continues on, what am I creating? Zinc oxide. So that's what I'm actually looking at there. Okay? So the mass increases. Good effort, though. And the reason why? It's going from zinc to zinc oxide, which has a greater mass. I think it's important to see that not everything is a total mind blow. Like, oh my gosh, like that isn't something that's over the top. I think we allow ourselves to overthink things a little bit too much. So that's it, 1 point for each part. To be totally honest, I don't think you have a chance at double I if you don't get I right. It's not like you say something else and, well, your answer really sounded really great, considering you had a wrong beginning part. C, the zinc air cell is taken to the top of a mountain where the air pressure is lower. I, will the cell potential be higher, lower, or the same as the cell potential at the lower elevation? And then, again, you have to justify your answer. I thought this one was much harder than the previous one, and just the fact that we don't talk about this as much. But I guess I'll say this. Focus on the idea of cell potential. So will it be able to run as long, or will it run less? So that's about concentrations of reactants and products. Like anything, a battery dies when it runs out of a difference in potential. And actually, a battery dies because it has reached equilibrium. Okay, so give it a thought. Think about what you would try to answer. Worst case scenario, you're wrong. Can we fix it? A reaction is all about this idea, and the thing is, you're not memorized, or you're not actually, I don't even think it's on our orange sheet anymore, the Nernst Equation. And the Nernst Equation allowed us to determine whether or not a reaction had more or less potential than it started with. But it all went down to the idea of Q, which is still products over reactants, when you are changing the amounts, okay? And if you increase or decrease that value, then you are either getting further away or closer to K. I like to think of it another way, is if I start to consume what I'm reacting, if I have less of what I'm consuming, the battery's going to, quote unquote, die faster. And if I pump more into my reactants in the beginning, then that can get consumed because I'm making the other cell, right? I'm producing the other cell. So that's the one that's not going to run out. So if you look at that and it says air pressure is lower, well, that also means that my pressure of my oxygen is also lower, which that's a concentration. Gas pressure is considered a concentration. So if I have less of that, then my potential will be less. I don't know if that makes sense, but it's going to be less because of that. And then you could go down a couple different paths. I honestly believe this is a slightly older question that I think that they would expect. They would maybe give us a little bit more because we don't have the Nernst equation on our reaction sheet any longer. But I would discuss the idea, bless you, that it would be closer to reaching equilibrium or that I have less reactants to react at this point. Something to that level of conversation. So that's ideas and thoughts about how a cell works in kind of a different way. But you got to realize that even if you're struggling, you're frustrated with electrochem questions, that sometimes electrochem questions start to not really sound like complete electrochem problems any longer. So it says metal air cells need to be lightweight for many applications in order to transfer more electrons with a smaller mass. You won't want to use zinc, that's pretty heavy in your ear. Sodium and calcium are investigated as potential anodes. A 1 gram anode of which of these metals would transfer more electrons, assuming that the anode is totally consumed during the lifetime of a cell? Justify your answer with calculation. So they're trying to push us towards calculating this, and we can have our answer with that. So here's the thing. You're going to have to talk about moles of electrons at some point. So a metal can become an ion. But I get to this problem like, I don't know what I'm doing right now. Like, I don't know. Well, then write down anything I know. So I know that I have 1 gram of, let's just pick one, sodium. Okay? And here's the key. I need to get to moles of electrons. Right? I mean, that's the idea here. So I'm just going to write this over here for a second. I need to get to moles of my electrons. So what I just start doing is I start converting. I just allow units to be your guide. So I don't want to cheat you from this. Can you get to moles of electrons from that? And then what you need to do is do it again. I think if you just start thinking, what can I put on the bottom? What can I put on the bottom? How can I make that equal? It's not as many steps as you think. So give it a shot. See what you can do. Try. You'll be amazed at what steps you can also come up with if you just actually write it down. But if you just try to visually do it, it doesn't always happen. If you're really stuck, I think the hardest part of it is usually just pulling that trigger of comparing electrons to my compound. So for every 1 mole of Na, or for every 1 mole of Ca, all you got to do is talk about how many electrons are lost in a normal situation where it becomes an ion. Okay? So Na would have a charge of 1, right? Plus 1. You got to know that. So that would be 1 mole of electrons because this is Na plus, give away 1. So then on the top of here would be 2 moles. Ca, because that would be Ca 2 plus. And that's really it. You can compare the atom to the number of electrons that would come off of it. And you do the math. Don't assume, I mean, you might have been able to assume, you just unfortunately still have to do a calculation, because this had 2 moles, that would probably give off more. I mean, it definitely has a better shot at it, but it also has to deal with how heavy it is and all that. So it's not just that simple. But the answer would be calcium, because it has more moles of electrons. And you're doing your, you get 1 point for the correct calculations of moles, and 1 point earned for taking. Oh my gosh. You got 1 point for converting this part right here. Just dividing by the molar mass. Whew. And then 1 point for the second part, doing 1 versus 2. That's amazing. Okay. Hey, I'm happy with it. Last part. Completely unrelated. Well, not unrelated. I should never say that. Everything's related, but it feels like it's unrelated to the kind of material that you're being asked. It says the only common oxide of zinc has a formula ZNO, which really doesn't mean anything with the next part of the question. Write the electron configuration of Zn atom in the ground state. So I will tell you this, in all AP questions, you have 2 options. You can do the whole electron configuration, or you can do the noble gas configuration. If you do the noble gas, be careful, don't skip something, because sometimes people skip things. And then the second part, I'd like you to do both these at once. It says, from which sublevel are electrons removed when a zinc atom in the ground state is oxidized. So when it says sublevel, you need to be very specific. You don't just do a number. You don't just do a letter. You would need both. You need a number and a letter. So give this a shot. Compare with someone else. Start it. I just go right through the periodic table. So I go through the S block. I go through the second part. So 2s2, 2p6, 3. I just start flying through it. Hopefully you're able to do that. So I go 1s2, 2s2. I go to the p's. I go back to the s's. I jump across to the p's. I'm on the fourth row, and then I got to go through the whole D block, which is one behind. Okay? If you did the noble gas, let's just review that quickly. If you did the noble gas, it's the noble gas from the previous row. So I'm on the fourth row, so that means I would take argon. And then what do? You take everything that's on that fourth row. So what's all on the fourth row? Or the fourth period, I should say. It's that and that, right? They're both there. But that has a 3, but it doesn't matter if that's on that row for the periodic table. So you could have done either one. Okay? 1 point though. Double-I, from which electron is removed, or sublevel, are the electrons removed from? So is it 4s or is it 3d? Where are electrons removed? They are removed from the outermost energy level. That's why they're called valence electrons. So don't get confused. I know why they're asking this. They're trying to confuse you and say, well, where were the last electrons placed? It doesn't matter. The last electrons, those 3Ds, are here. Those 4S's are here. That's how you want to envision that. So the electrons are always in the outermost energy level. So if it was a 4s2, 3d10, 4p1, it'd be removed from the 4p first. But it would be all of them. It would also be the 4s. But in this case, it would be the 4s. It's the outermost energy level. Okay? So be very, very careful on that. All right, and that's the end of that problem. And that was 2015, so pretty recent. A lot of stuff going on in that one. Okay, we changed gears. And I like this problem because it just kind of reinforces. I think students are really troubled a lot on the actual exam, getting confused of pulling the trigger on not very complicated calculations, but ones that seem to confuse them. So I thought this was one that is good. So it says you have a sample of solid lead 2 nitrate, and it's added to sodium iodide solution. Assume no change of volume. The solution in a chemical reaction takes place represented below. And here it is. A. List an appropriate observation that provides evidence of a chemical reaction between the two compounds. That's all it says. Now, if they just explain this to you, you would have to, I don't know, figure out what happened. But they already gave you what happened. So, can you say something that makes sense? Because there are other questions like this on exams all the time. Like, list an observation that you would have in lab that could prove that the reaction occurs. Well, things like color change, things like heat or light, things like gas, and what is this one? A precipitate formed. So what you would have said, now be careful, you want the really good answer is that a different solid form than existed initially, because there is a solid there. But a precipitate form, exactly what it is. So you would have witnessed a precipitate. Okay? So I just said the 4 signs of chemical reactions. Heat or light, it's gas. We just did precipitate, and if a color change happens. Well, they don't talk about any of those other ones. So if a solid shows up, a precipitate forms. Even if you're like, but it's always AQ. A new solid was created. So, and I know what you're thinking if you're looking at that and going, whoa, that's nitrate. Well, it's a solid in the beginning. So that's why it's not in a solution yet. So that's why it's a solid. All right, B. And that's proud. Thank God. That's only one. Calculate the number of moles of each reactant. Okay, so this is what they do. And I'm going to let you do it, but they give you the information in 2 different ways. So they give you some information like that, and they give you some information like that. And they want moles of both. So you know that this is 2 points because it's 2 different kinds of problems. So you need to find moles in 2 different ways. Please do that. compare with someone else if you'd like, but try to figure that out. So as you're finishing up the first one, they give me it in grams. So I know I can get from grams to moles quite easily. Second one, a little different. They give me volume and molarity. Not any harder, just different. What I would do is this. And you can write it in many different ways. But always understand molarity is moles over liters. And there's my NaI. Okay, so just recognize that all they're doing is trying to see if you understand how to convert to moles in some different kinds of situations. Nothing more. C, they did this for a reason. These definitely could be I's, double I's, triple I's. It's all leading into it. Identify the limiting reactant. Show calculations to support your identification. So what I need to do is figure out which one runs out. That's all. So what I would do is probably just grab one of them. It doesn't matter which one. And compare it with the other one using mole ratios, right? For every one of these, I have two of these. So I just have to grab one. And it doesn't really matter which one you grab. I always grab the first one I calculate personally. So I can just take this. And now I'm saying for every one of these, I have two of my NaI. If it reacts perfectly. So that's how much I would need. I have a lot more than that. And I know some of you could have looked at that, well, my gosh, I need twice the amount of that, and I have more than twice. It's fine, but you have to show it because it asks for it with the calculation. So you have to have that. So my limiting reactant is definitely PB NO3(2). Because I have more than I need. I have that much. I only needed that much. If you did the other one, you wouldn't have had enough of the PB. Please though at the ending of it, don't write limiting reactant at the end. People do this all the time, write NI or LR right here because they're talking about that. But your answer is NaI. So you can't be talking about PB NO3(2) if you talk about the answer. Okay, that's actually 2 points. Wow. 1 point is earned for the identification of PB NO3, 1 point is earned for justification in terms of relative moles. So if you had written needed, you might want to say, it might not be a bad idea to just say and compare it, say that I have more than I need. I think that would be enough. I really do. So let's see. I'm just excited to get to this one. D though, we gotta do something else first. Calculate the molar concentration of NO3 minus in the mixture after the reaction is complete. Whoa, okay. After the reaction is complete. So this is important. NO3 minus, first off, if you understand this, starts as a solid, goes in a solution, and then stays as a solution. NO3 minus is usually what we call a spectator ion. So I'm not really worried about it being consumed. I just want to talk about how much I had of it, and then I need to make sure I get it into a concentration. So I think a lot of people are going to get confused by this part, but NO3 never was taken out of solution. Okay, it dissolved and stayed in solution. So I still have it all. Like it's all as AQ. So this all can be calculated as molarity. All right, so here's the key. You got to make sure you use the right amount. So how many moles of NO3 do I have? Well, it all stems from this blue right here, right? This is the amount of moles of PB NO3 do anything with that. I want NO3 minus ion. So I want the concentration of NO3 minus. There's the letter D. So I want moles over liters. Okay, so let's talk. I can do one that's much easier. It seems that I have 125 milliliters. That's it. Because it said that adding this doesn't change the volume. So that's my volume. Good. Okay. What's my moles? Well, let me write down what I was given and what I figured out. Maybe that's enough. This is from the calculation in letter B. But that's the source from PbNO3 too. Is that right? The way I'm asking this. Probably not. Dustin, what's wrong with it? So I need to. You need to double it because what happens, this is a good review, when this breaks apart, although honestly the problem with this is that PB doesn't go in the solution, but let's pretend it did for a moment, is that this comes out like this. And every one of those ions carries the exact same molarity or the exact same number of moles with it. Okay, so they all have 4.53 times 10 to the negative 4 moles at that moment. So you got to make sure you take that into account. It's always good to review that. So I calculate that. You all can punch that easily in your calculator. This is the answer that I would get. You can put in scientific notation. That's perfectly okay. 1 point is earned for the correct NO3 minus amount. So did you double it? And then 1 point is earned for the correct molarity. So this I love. Last question. And it's normally not given like this long. It's actually, the actual question has these three and then these two below it, and they're much, much bigger. So I hope you can see it. So circle the diagram below that best result or represents the results after the mixture reacts as completely as possible. So the reaction is basically over. Okay. Explain the reasoning used in making your choice. Okay. So you can see there's a bunch of different things here. My suggestion, and I don't think it's a bad idea at all to work with someone else on this. What can you get rid of, or what do you know is a simple truth or something that you feel really confident on that has to be present or can't be present? Eliminate those first. Then what you need to start thinking about is potentially, it's not always the case, but maybe the sheer amount of something. Maybe that has too many. Or maybe, again, it might just come down to this can't be there or this has to be there. So give it a little time. These aren't the easiest in the world. Start crossing ones off that you're sure on, and then let's see where we're at. If you are good to go, you need to give a quick, like, one-sentence explanation of why you picked it. What's the easiest one to get rid of? First one, there is a precipitate, right? Okay, see you later. All right, what's another one? Give me a reason why I could get rid of another one. Harrison?
The last one is because it says the solid forms is PbNO3.
Nice, I actually didn't notice that. Nice. Yeah, that's not the precipitate, right? I mean, and if you're like, well, but it's right there. But this is when it's complete. So we aren't in that right mindset. Good. So now we're down to 3. So now it's going to get a little more specific, right? Because now we can't use the precipitate any longer because they're all the same. So now it's about the ions present. Right? That's really what it's about. So there's one more that, well, there's 2 more that we have to get rid of, but there's one more that I thought was really easy that stood out to me.
The second to last one, because PbNO3 is the
Are you talking about this one?
Yeah.
Okay.
PbNO3 is the limiting reactant, so the P has to project, so I can't say.
So this is the limiting reactant. Now, technically, the nitrate also was part of that limiting reactant, but the Pb was in as a precipitate, right? And that's why the reaction stopped. So I actually agree. Cannot have any Pb in there. So does any of these other ones have Pb?
No.
Okay. Okay. So we can't use that. So then there's only one more thing in here. What's the difference between these last 2? What do you notice? What is the difference? What does it have? I believe it has I versus no I, right? Okay. So here's the key to that. Can it have I in it? go back to the math and you look just for a moment, right here, it says that we need this much NaI. And how much yes. And how much NaI do we have? We have it in red. We have quite a bit more NaI, correct? So, because there's so much more NaI, that the PD is going to react with all the I, but the difference between these still results in I still being present. So, if you chose this one, you are correct. There is excess I still present because it was in such excess. And that is difficult. So 1 point is earned for the selection, and then 1 point is earned for the correct rationale. So I will read actually what it says. PbI2 precipitates, and PbNO3 is the limiting reactant. So there's essentially no Pb2 plus in solution. Because there was so much NaI in excess, some of the I minus remains in solution along with the Na plus and NO minus, or NO3 minus. Okay, I like those. I think they're hard, but I think they're good to learn from and to get familiar with, because they're doing this more and more every year. Problems like this. All right, we'll do one more and then we'll take a little break. This is a short problem. Let's see how well we do on this. So it says answer the following questions about solubility of CaOH2. And they give us a KSP of 1.3 times 10 negative 6. Please do not have a mindset of, oh, no, not KSP. We tackled enough, hopefully we can handle it. So A, write a balanced chemical equation for the dissolution of CaOH2 in pure water. And then, well, we'll get to B. So can you do A? Let's do that. A lot of people, you're not doing this enough and reviewing enough. You think about the water. If it's dissolution means dissolving, it's just going from a solid to its ions. It's got to be completely balanced. You do not need states. I'm just putting the states for you. And if you didn't put a 2 there, you don't get the points. Sure, it's balanced. Okay. B, calculate the molar solubility of CaOH2 in 0.1 molar of CaNO3 Okay, first, let's just take a step back. I just asked what is the molar solubility. This is what you would have done. You would have said, okay, fine, like this is 0, 0, so this is basically plus x plus 2x, so x, 2x. What I would have done is my KSP. I want to do all this because I want to show you the difference here. That this would have been x times 2x squared. Ultimately, this would have been 4x cubed, right? I find x, and x is my molar solubility. We did one of those yesterday. We did a molar solubility. Here's the trick. They say there's something else in there already. So whenever I'm doing a K problem, I'm thinking about, and they made me do this on purpose, they've already helped me start my icebox. Think about icebox. Well, what is this? This is a salt. So this is going to break up into Ca2 plus and NO3 minus. And there's going to be 2 of them. So what I'm going to think about, I'm just going to erase this and reapply the same idea. And instead now is that I have 0.1 of this and 0 of that. And you're like, well, I don't know what to do. Everything else is the same. Okay, it's still going to go this way because it's 0. So this is still plus 2x. This is still plus x. Let me just show you the difference. So it would look like that. So now I just plug that in. I should have even erased my other part so you could have seen how it looked. It looked just like that. And what do we do? Now, remember what we had? We had 4x cubed. What do we do with x's that are added or subtracted in an equilibrium expression? We cross them off. Okay? So if I cross that off, now I have 1 less x. So this is going to change this. It's called the common ion effect. If I have some in there already, not as much can dissolve because there's already some in there. So it's going to slow that process down. So whatever x is going to be is my answer still, because x is always the molar solubility of the whole compound. Because it's of 1, it's reflecting a ratio of 1. So please solve for it. Go for it, please. very official here. I don't know if you'd have to rewrite it. The trick is like X, what is X? You haven't really said it's molar solubility. I don't want you to start getting too worried about all your answers, but it is the same thing because X is reflecting the overall compound. Okay, so that is how much could dissolve. You're out, what the heck are you saying, molar solubility? What is the molarity of the saturated solution that could dissolve? I love this question as well. The visual stuff I like because it's showing that you understand something. And usually if you practice this enough, they're not as hard as some other things. It says in the box below, complete a particle representation diagram that includes 4. I looked through this. The amount of people that didn't use 4, you're done. 4 water molecules with proper orientation around the Ca2+ ion represent the water molecules as Mickey Mouse. So you got to make sure that you draw it just like that. Okay? I'm not saying anything. I have done this in front of you so many times. I did this last night multiple times. You need to draw 4 water molecules surrounding the Ca2+, and those are my water molecules. Can you do it? Go for it. What's the key to this? Water surrounds ions. Ions and salts are soluble because water and ions can interact because of the charges. So if I have a positive ion, what do I want with the water? I want the negative, and the negative will be the big one, the oxygen, pointing towards it. So as long as you drew 4 of them, it doesn't have to be exactly on each side. As long as you're doing that, that is correct. If it was a negative, the hydrogens would be pointing towards them. So here's my, it would look like that. If it was a positive ion, here we are. Oops, what am I doing? What am I doing? There we go. Those would be my 2 options. Oxygens are attracted to the negative, the hydrogens are attracted to the positive. It's just a point, but that's how we would do that. Okay. So, another classic lab problem. I will try to always have these in the reviews as we get to the end because it's important that we are just understanding the simple information that's given to us. So, in this case, they give us a data table first. It says students given the task of determining the I- content of tablets that contain Ki in an inert water-soluble sugar as a filler. The tablet is dissolved in 15 milliliters of distilled. So, by the way, the tablet has some iodine in it, or some Ki in it, and then the rest of it's just sugar. Sorry, it's dissolved with excess lead nitrate. A yellow precipitate forms, which is then filtered, washed, and dried. The data from the experiment are shown in the table above. So we have a mass thoroughly dried filter paper, mass of filter paper, and the precipitate after first drying, after second drying, after third drying. It doesn't mean you have to understand everything about the problem after you read the intro. It'll give it context as we go. Here we go. A, for the chemical reaction that occurs when the precipitate forms, I, write a balanced net ionic equation for the reaction, and double I, explain why the reaction is best represented by a net ionic equation. So, you need to think about what was given to you in the paragraph, and you need to come up with a net ionic equation. Easier said than done. So, work with each other or yourselves. What is the net ionic equation from what is being described in the paragraphs? Not in the data table, I'll tell you that. That might help you. Those are my 2 reactants. Looks a lot like a double replacement reaction. that was my balanced equation. Okay, what's my precipitate in this? Good. So whatever's changed is probably going to be my net ionic. So if you remember from way in the beginning of the year, the easiest way to do this is if you know there's a precipitate, you write that first, and then you write the ions that make that precipitate. That's truly what would happen. So this is what I would have for my net ionic equation. Why aren't the other ones included? Because if I went through it all, this is AQ, the NO3 is AQ, it's still AQ. The K is AQ, like these are all AQ right here on the left. This is AQ, this is AQ, this is AQ, and this is the solid. So my Ks are still AQ, my NO3s are still AQ. So that actually leads into why I write a net ionic. And I haven't read the answer yet, but you could say that only the species that are involved in the actual chemistry, or the ions and the precipitate, I like to just say species because then you're saying everything, that are involved in making the precipitate or the new compound are only shown, while the ions, K plus and NO3, are only spectator ions. They're not involved in the chemistry, because they're doing nothing. They're literally watching the entire time. They're not involved. What they wrote, just so you hear, the net ionic equation shows the formation of PbI2 from Pb2 plus and I minus, omitting the non-reacting species, K plus and NO3 minus. B, explain the purpose of drying and weighing the filter paper with the precipitate 3 times. What are we doing? Why are we drying it 3 times? To ensure, maybe that's not the way you would went, but I'm trying to ensure what? All of the water has been removed, right? Why 3? Because after the second, I mean, they could have asked this, why did it have to be 3 times? Because after the first time, after the second, it changed. So they needed to check one more time. Now, if you're sitting there and going, well, it changed again. Yeah, it did. By by a very small margin. Like a thousandth of a gram. So it basically shows me that the water is not all gone. Okay? So filter paper and the precipitate must be dried several times to ensure that all the water has been driven off. Or all the water has been removed. Okay? So whenever you see that, that's not common. It's like the third time we've seen a problem like that. So to ensure all the water. All right, C. In the filtrate solution, is K plus greater than, less than, or equal to NO3 minus? Justify. Sometimes it's not about calculation. Honestly, if you look at this, they don't give you enough information potentially of how much you started with, and it may not be needed. It's not asking for an exact amount, it's just saying greater than, less than, or equal to. So, when I was going through this problem, just to speed things up a little bit here, the key to this was sometimes just recognizing which one you have more of in the beginning. So if I go back through my problem, which one in the paragraph is stating that I have more of it? K plus or NO3 minus? Can you find it? I have more, the key word in there. Excess. I have excess. That means I have more than I need. Plus, what's going on with the NO3? There's a 2 on it, right? So doesn't that even mean I have double the amount of my excess? So all you have to do though is go off the excess. So you would just say simply that the K plus concentration is less than, or you could do a less than sign. It's an excess. I mean, that is a huge word. Don't ever take that lightly. If some problem goes out of their way to say something's an excess, then you already know what's limiting, you already know what's going to run out, you already know what you have left over in a problem. They've already done work for you that they are not going to ask you about any longer. Their answer is going to be similar. K plus is less than NO3 because the source of the NO3 minus 8.2 molar PbNO32 was added in excess. Okay, so there hasn't been a lot of things yet in this problem. But then here we go. D, calculate the number of moles of precipitate that is produced in the experiment. So now they want a little bit of math. All right, so what you need to do is realize, okay, I need to start with the precipitate, and then I need to get to moles. So where am I going to find that? Probably somewhere up in here, somewhere in my data. Okay, so see if you can figure that out. How can you interpret that? Get to moles of my precipitate. I'm just looking at my data. This is the mass of filter paper and precipitate after third drying. I want to use that one. But then I want to get rid of the filter paper. I'm not in love with the wording that they had on that. Like a lot of times they just say mass of filter paper. So don't let that confuse you there, but that I need to get rid of, right? I need to get rid of those to have only the precipitate left. So I want to show that. That potentially could be points. And I want to make sure that I'm doing it correctly anyway. So I have, and now it's just a step. I'm in grams, I just want moles. That's all it's asking. So just make sure you add it up correctly. Honestly, some of you have done 3 practice tests now. For most of us, we have a little bit of time left, so I don't know. If it's molar mass and it's not a number that I normally have seen, I might just quickly type it in one more time. It is the one thing that I will make the biggest mistakes on over time, not because I don't know how to do it, because I'm just going fast through it. I'm not really thinking about it. And if you see a number that you're just like, oh, I haven't done a 461 molar mass too often. You might just want to punch it in one more time just to make sure that you have the right answer, because that would be a shame that you get it wrong because of calculator issues. And it's only a point, but it's still a point. So now, here's where it gets tricky. It's asking for, let's go back down, calculate the mass percent of I in the tablet. So let's make sure you understand what that means. That means you want the mass of the I over the grams of the tablet. That's what that means. You have to understand what you're looking for to actually find it. Okay, so some things you might already have, some things we need to discover. All right, so I'm going to go up top, though, to find this, just because I have some other information that I already have. And I just erased something I really need. Okay, let's bring something back. I like that equation. Always good to have equation. I like working with equations. All right, so this is E. So use what you have. Think about what you've been asked to do already. If I need grams of I minus, what do I have right now? I have moles of PbI2. Realize that you have moles of this, and you want grams of that. We can do that. Right? That's just stoichiometry. It's truly just stoichiometry then. Okay, so get there, please. And then finish this idea up. Grams over tablet. That's what that would be asking. So those of you that wouldn't recognize, I don't know where to go with that. I'm using what I already have. I'm doing it in the context. And where do I always go back to? My balanced chemical equation. All the time. So just by doing stoichiometry, right? I'm in moles of something, I gotta do the mole ratio to get to the other thing. Other species, I multiply by the molar mass, get back in the grams, and there is my grams of my I minus. What is the mass of my tablet? Did you find it? Did anybody find it? Paige, what's the mass of my tablet? Yeah, it's that, isn't it the top? I think it's the first one. Not gonna lie, it took me a while. I thought it was in the paragraph. My mind, I didn't see it above that. I'm like, well, why would it be? I was looking everywhere for it. And I'm like, oh my gosh, it's sitting there. So it's there. It's got to be there. But it took me a while to find it. But I knew that it had to be given to me. So no. So I hope most of you found that right away. For some reason, it was not clicking in my brain. I just could not see it. It says a percent, so make sure eventually it is a percent. You don't have to show the decimal beforehand. If you calculate it and then just put it into a percentage, it is asking for a percent. So that is percent mass. Percent mass is always the amount of the part you have over the mass of the whole. So they went out of their way to actually say it. The mass percent of the I minus in the tablet. So that would be 30.6%. Almost done. This is a pretty long question. When you're getting to G's, you've been working on a lot. G. No. F. I'm not even there. Oh. In another trial, a student dissolves a tablet in 55 mils instead of 50. So I'm adding a little more water. Again, you don't have to do this. I'm not saying that you need to, but if you ever are stuck, you could always do this. Like, okay, now it's 55. Like if you cannot visualize it, draw it as you're reading it or right after, if that helps. Predict whether the experimentally determined mass percent of I minus will be greater than, less than, or equal to the amount calculated in part B. Justify your answer. So, I believe we already talked about this. Is that this was added in excess. Okay, it does not say justify your answer in the calculation. So when it's not a calculation, it's more of an idea. And it's more about you just understanding it. So if that's in excess, that means the other item is in a limiting fashion, right? So I have a certain amount of I in there no matter what, right? And then you drop the tablet in, and then what did we do? And what was the whole point? What is all this? What are they doing? They are getting rid of the water. So it doesn't matter how much water I have because isn't the I minus going to be sitting there at the end anyway? That's all it's saying. I added more water. That doesn't affect my tablet. My tablet dissolved in the water. I dried out the tablet. It wasn't a concentration question. Yeah, you dissolve it in water and you have more water, the concentration is going to go down. I think that's what they're hoping students are going to say if they're going to get a wrong answer. But this is not about that because you were filtering it out and drying it. So the mass percent will be the same. PB2 plus was added in excess, determine that essentially no I minus remain in solution. Additionally, water is removed by filtration and drying, leaving the same mass of the dry precipitate. Like, I guess the key part of that was that all the I was already precipitated in the first place. So adding more water doesn't matter. It was still going to precipitate because the other stuff was in excess. And we're drying it out. I'm not going to write the whole thing. Okay, finishing up. I made it with a G. A student in another lab also wants to determine the I minus content of a Ki tablet, but does not have access to lead nitrate. However, the student does have access to silver nitrate, which is so much more expensive. Which reacts with the I minus to produce AgI. The value of the KSP for the AgI is 8.5 times 10 to the negative 17. I. Will a substitution of AgNO3 for PbNO3 result in the precipitation of I minus ion from the solution? Justify your answer. Okay. All it's basically saying, will this make it precipitate? How do we know that things that are going to precipitate if they have a very low KSP? That's why on all your solubility rules, by the way, you probably knew your solubility rules. Say, well, halogens with silver and lead are insoluble. Well, the reason why they're insoluble mathematically is that they have very small KSPs. So because they gave it to me, all I would say is, yeah, it's going to precipitate because that's a very small KSP. And you're like, well, how do you know it's a very small KSP? Well, again, let's just remind ourselves what this means, that if I drop that into a solution, this value right here is times 10 to the negative 17th, meaning that my reactants are extremely favored, right? Extremely favored. Like the products aren't favored at all. So as little as possible is going to result. Okay, so that would be more or less the answer to that first part. It would be nice to hear what it says. It says, yes, addition of an excess of 0.2 molar AgNO3 will precipitate all the I- ions present in the solution because AgI is insoluble as evidenced by its low value KSP. Last part. The student only has access to one Ki tablet and a balance that can measure to the nearest 0.01 gram. Will the student be able to determine the mass of AgI produced to 3 sig figs? Justify your answer. Okay. You can't just say no because this is 2 sig figs. Okay? Because how could 3 sig figs be present? Let's just, like if I have this, I'm making up a value here, but that's 3 sig figs, right? So, how does this, if this isn't going to be 3 sig figs, the number has to be what? Like I can't go past this. So that to be less than 3 sig figs, the number has to be less than 1 gram, right? Because if it's this, I know this isn't an answer. That's only 2 sig figs. So all you got to do is go back at your other data and just see, am I greater than 1 gram of my compound? And if you look, where did we just do that? Can we do it right here in letter E? Right? It's going to be similar. It's not close. It's going to be extremely similar. So the very fact, I would say, is that because the precipitate is going to result in less than 1 gram, we will not be able to have 3 sig figs because it only goes to the 100th spot. That's it. That's all that this means. It's a weird, honestly, it's kind of a weird question. It's like, oh, guess I'm talking about sig figs all of a sudden. So I don't know if that makes sense to you. It's no, if the masses can be measured to plus or minus 0.01 gram, then the mass of the dry AgI precipitate, which is less than 1 gram, will be known to only 2 sig figs. So you do have to make a little bit of an assumption because you haven't done the math on that. But, I mean, it's very similar. You could have done the math. They do tell you that it's 0.2 molar of AgNO3. But at best, not even thinking about the mole ratios, at best, this is going to be double that or half of that, right? I mean, with the mole ratio issue. So, not enough. Okay, good. Now move on. 2 left. We'll move on. These are both not quite as long as that one, for sure. All right, this one's kind of funny. This one's from 2014. It says, gives you an equation. When it's above everything else, that means that it can be used the whole time. It says, when heated calcium carbonate decomposes according to the equation above, in the study of decomposition, calcium carbonate, student added 50 grams sample powder of CaCO3. The student sealed the container, pumped out all the gas, and then heated the container. As the container was heated, the total pressure of CO2 in the container is measured over time. The data was plotted below. Weird, it seems familiar. Student repeated the experiment, but this time the student used 100 grams of the sample of powdered CaCO3. In this experiment, the final pressure in the container was 1.04 atm, which was the same final pressure as the first experiment. So just hold on, I want to make sure I understand the difference here. The first time they used 50 grams. Sometimes I like to write it down to understand the difference. That was the first time, that's what it said right here, and this was the second time. A, calculate the number of moles of CO2 present in the container after 20 minutes of heating. So after 20 minutes of heating, the only reason why they wrote a time here is you just look at the graph, 20 minutes, oh, it's right here. Oh, that's, I'm assuming, is what they told me. That makes a lot of sense. Where is it? 1.0. I mean, that's got to be 1.04, right? It's just over 1. So, your first instinct's got to be, is this ideal gas law? Have they given me enough for that? Well, I got my P. my T. Do I have a V? We need 3. I do somewhere, don't I? Oh, here it is, right here. So I do. So do it. I've been saying over and over again, these are always worth 2 points, and like the last 3 that I said now are only worth 1. I know what's happening. It's only 1 point. 1 point is earned for the proper setup using the ideal gas law and an answer that's consistent with the setup. So I don't quite know what that means. Like if your setup was totally wrong and you got an answer consistent with what you messed up on, not sure. I don't think you did it right if you didn't have that. So there's my number of moles of CO2. B, very interesting question. So the student claimed that the final pressure in the container in each experiment became constant because all of the CaCO3, so all of this had decomposed, meaning all of it went to the other side. Based on the data in the experiments, do you agree with this claim? Explain. Okay. We could talk about this for a while, but to me, there's a big hint here. They give 2 answers. One, they do a bunch of math. The other one, they don't. This was where I went right away. Here's the thing. They did 2 experiments. One they did with 50 grams, and one they did with 100 grams, and both of them, this is the only gas, and both of them ended up with that. If a reaction's ending up with the same pressure each time, what have we reached? We've reached an equilibrium. Wouldn't it make sense is if 50 grams all decomposed and it made a certain pressure, and then 100 grams of it all decomposed, wouldn't it make more pressure? And to me, that would, right? I'm going to make more of it because I have more of it. So that to me is evidence that it does not all decompose, because by using different amounts of CaCO3, I reached the same pressure both times. So all of it could not have decomposed. But I don't know how else to say it without trying to get technical and overly fancy and not needing to go down paths. That's what's happening. I would make more pressure if all of it's being consumed, but apparently I'm not. That double arrow is not a bad little help too. Hey, thank you, double arrow. That's not an explanation, by the way. No, because of the double arrow. I will read what they have. I'm sure it's going to be similar to what I said. So the 2 different experiments, one was 50 grams and the other with 100 grams of CaCO3, reached the same constant final pressure of 1.04 atm. Since increasing the amount of reactant did not produce more product, there is no way that all of the CaCO3 reacted. Instead, an equilibrium condition had been achieved, and there must be some solid of CaCO3 in the container. So that's a single point. But I guess to me that makes sense to me that it makes the same pressure each time. And it couldn't have used it all up. Okay, as we're finishing that up, letter C. After 20 minutes, some CO2 was injected into the container. Okay, so after 20 minutes, so here we go. I'm right here, and now I'm putting in some more CO2, and this is basically all CO2. And how do I know that? Because that's the only gas in this equation. The other ones are both solids. Initially raising the pressure to 1.5 atm. Would the final pressure inside the container be less than, greater than, or equal to 1.04 atm? Explain your reasoning. So if you had to draw this, by the way, we can't even do it. Literally what it would do is it would have done this. Now what it's asking after that point, will the final pressure be greater than, less than, assuming they gave all the options, or equal to 1.04 after I did that? Explain the reason. So, any gut feelings? What do you think? Equal to. Yeah, because the equilibrium condition, or the condition of equilibrium, was already 1.04. So what does all reactions do? They settle out. They find their way, right? You don't have to talk about how it's going to go back left or right, but what is going to happen, guys, let's just stop writing for a moment. Just look. If I add more, isn't it going to drive it back to the left? So it's going to then consume the CO2 to re-establish equilibrium. So this is a sneaky equilibrium problem that was snuck in here without writing any K values. This is an equilibrium problem. Okay? So that, I mean, you could have talked about it in that way. Well, according to Le Chatelier's, adding more of the CO2 will cause the reaction to drive it back to the left until it reaches 1.04. But you could have also said equilibrium has been established in two other reactions at 1.04. So over time, this too will also reestablish equilibrium at 1.04 again. I will relook at that. The final pressure would be equal to 1.04. Equilibrium was reached in both experiments. The equilibrium pressure, sometimes I'm really wrong. As this temperature is 1.04, as the reaction shifts toward the reactant, the amount of CO2 in the container will decrease until the pressure returns to 1.04. Okay. One left, I believe. Are there sufficient data obtained in the experiments to determine the value of the equilibrium constant Kp? So I want Kp. For the decomposition of CaCO3 at 1100 Kelvin. So, you know what? Better question. What would Kb equal? The expression. What would my Kp equal? It would be on the top. Anything else? No, because we do have gases for pressures, right? If this was a reactant, it would look like that, right? So, if that's the case, do I have enough data? I do, because the value for my equilibrium at my value at equilibrium is 1.04. So yes. So that's actually how I would have done it. I'm just like, well, what is my Kp? What is my expression? Oh, that's what this looks like. So what's weird is my K is 1.04, which is kind of a weird number to have, like, because you're feeling like that was a pressure the whole time. So it is favored, but it's greater than 1, not by a lot. It is. And that's it. So you do have enough information. It just doesn't seem like we do. But as a reminder, in all equilibrium expressions, it's always gases or AQ solutions that are in my equilibrium expression. And that's it. So that was only a point. So this is only a 4-point problem. It looked like a lot bigger problem than it was. So we end with a problem that I know we need to see one more time. And I know that we just did a electrochem to start, but I thought that I need to see, we need to do letter P one more time. So I thought this was a good one. I haven't done this kind of a problem in a very long time. Honestly, I slightly pray that you don't have to do this, but if you do, I'm glad at least we did this. So they give you a picture. Right away, I hope you're seeing that. Okay? Big deal. It does not say voltmeter. It says power supply. So that's something very, very different. Okay? It says an external direct current, DC instead of AC, power supply is connected to 2 platinum electrodes. Why platinum? Those are inert and they allow other compounds or other species to react or be reduced or oxidized. Immersed in a beaker containing copper sulfate. So the solution, it's just in one cell of copper sulfate, as shown in the diagram below. As the cell operates, copper metal is deposited, another way of saying plated, is how we plate things, electroplate, onto one of the electrodes. So the one on the left, they are indicating. And oxygen is produced on the other electrode. Look at those beautiful bubbles. The 2 reduction half reactions for the overall reaction that occurs in the cell are shown in the table below. A, on the diagram, indicate the direction of the electron flow in the wire. Okay, so you feel like you haven't been given a lot of information, but they've given you more than you need. So let's just think about this. They're saying that the copper is being plated, okay? And they're also saying that the oxygen is being created on here. So you could look at those equations this way, but they've gone out of their way to literally write this equation here. So they're making copper onto this. So when the electron is on that side, are the electrons going to this electrode then, or away from that electrode? Gaining it, right? Like literally, this is how you add something, right? Second, first grade, that's how we add. This plus this, oh, I gained it. So because of that, my electrons should be flowing towards the copper. I think it literally told me to draw it on there. If you don't like it like that, I know whenever I'm drawing it with you guys, I'm being very nice and exact. But that's what it looks like. Okay, so it's telling me that, it's gaining it. Okay, well that's a big piece of information. So that's just one point. Letter B, write the balanced net ionic equation for the electrolysis. This is very different than a voltaic or galvanic cell, like a AA battery. This is not naturally occurring. That occurs in a cell. Okay, they give you two of these. One of them has to flip. Well, they've already established. They went out of their way. They helped me. So this one has to stay like this. The other one has to flip. You know what, though? Let's say you didn't know. Let's pretend they didn't give this to you. Okay? I want to go back to this for a second. They say electrolysis, or they say external power supply, and the very fact that it has a power supply right there, all of these things. What do I know about my voltage? What does it have to be? Like overall, my voltage would be negative. Because what does a positive voltage mean? That it naturally is giving me energy, right? A battery, you plug it in, it's giving me energy. If it's being powered by a battery or electrolysis, it's the opposite. So this would be a negative voltage. So you would have to make this negative. If you did not know and they did not establish an equation for you, you just got to look at that and go, okay, I got to flip the one that makes this negative. That's all. Don't start memorizing, you always flip the most positive or the most negative. Just, I flip one or I flip the other and I add them together. Which one gives me the most negative value? And in this case, I hope it makes sense. I would flip the 1.23, right? So I'm actually going to rewrite it once, just up here. I mean, you can write right on yours if you'd like. But I want to just see it. And then I have this below it. So it's asking for the net ionic. Don't let that confuse you. That could just be all of that added, because these are kind of half net ionic equations already. So I'm going to add these all up. Before I add them up, what do I need to do? Always, my electrons need to equal, right? I cannot add these up without electrons being equal. So this would have to be a 2. This is a 4. This would be a 2. That is what they're seeing. They're seeing if you're understanding, you're flipping the proper one, and you're using the right number of electrons. I'm going to go out on the limb and yes, and say that the electrons are probably one of the points. Not quite, but close. So then my answer would look something like this. Doesn't matter the order. They have unique ways of getting points. 1 point is earned for all 3 products. So if you figured out what the products were, and then 1 point is earned for balancing the equation. Right? So they basically, did you multiply that by 2? I would have rather it said that you recognize that they both have 4 electrons, but I get what they're doing. C. And these are all good questions regardless. So if you're understanding that this isn't a natural battery, you should be able to answer most of these right away. Predict the algebraic sign of change in G for the reaction. Specify your prediction. So G will be positive, and then all we got to say is because it's not spontaneous. That's it. This is not a naturally occurring process. So change in G and honestly, I would actually say one thing more. Because the voltage is negative and not a spontaneous reaction. I mean, I haven't read what they have. That would be like hammering it home because of the fact of the voltage. And I went too far. The sign of change in G would be positive because the reaction is not spontaneous. Stop One point is there for indicating that change in G is greater than 0 and supplying it correctly. All right. We're doing well. D, calculate the change in G. Calculate the change in G. So what do you use for that? It's the same one every time when we have electrochem problems. You might even have it memorized, maybe accidentally. Or you look. It's NFE. It's this one. Personally, I find it to make sure I see it. It's one of those things where just being familiar. So we plug this in. So let's make sure that we're plugging this in correctly. The N is the moles of my electrons. My F is already given to me. It's like 96,500. I think on your sheet's 96,485. And then where did I get E from? My addition of my cell. So I might need to do that. At some point, if I haven't done it yet, don't ever come up with a number that's important in a reaction without showing how you got it. Seriously. So what I would have done is something like this. I did flip that one, yes I did. So my negative 0.89 volts, I want to show that. And actually, that's where the point. I'm just doing that one. Just getting that. So then what's my N? What is it? It's going to be 4. I needed 4 because that's the least common multiple between those. So I have 4, approximately 96,500. It's coulombs per mole. And then negative 89.89 volts. It does not ask for a unit. So you will actually get lucky with this if you are, but I need to stress that on the bottom of your electrochem section, it says 1 volt equals a joule over coulomb, 1 joule over 1 coulomb. It's there. So it just recognizes to you that this is in joules. That's what you need to just realize, okay? So the answer is approximately, I'm sure it's not exactly this. You should feel good that that's positive. If you got a negative number, you're just contradicting what you said. You said that G is positive, so it better be. And if you're going to write just positive signs, which I did not like that I did that, you might want to put quotations because that positive, I will even say when I'm grading a test sometimes, I'm like, T, what the, like, you're going really fast through it. Just be careful. Okay, so this is why, one of the reasons, besides the fact that I did want to talk about the difference between these, is E. It says an electric current of 1.5 amps passes through a cell for 40 minutes. Okay, now, I am pretty sure that it tells you what an amp is on your sheet. At least I think it did. No, on the side. Like in the IQT problem. So see how it says current is I, and then it says amperes? So if you're looking at your sheet, okay. I want to make sure you understand this. So it says that amps is I, and then all you got to do is look right below it and see what Q and T is. And isn't Q coulombs? And T is time or seconds. I don't know if it does actually say seconds. So that means amps is coulombs per second. Like, bless you. Again, it shows that on that sheet. I think that's important. So here it is. I want to get 2 grams of Cu. So let's just talk about what I have. I have 1.50 coulombs per second, and here I have 40 minutes. Those are the only 2 pieces of information I have. My experiences with every T-chart I've ever done is if I'm given 2 different values and one of them only has 1 unit and the other one has 2, the smoothest T-chart is starting with the one that has 1 unit, because everything else then can cancel out really smoothly. You're not dead in the water going to be wrong if you chose differently, but if you did this, you probably have a better shot at it. So what I did when I solved for this earlier today, I actually just wrote the two values I have first. Okay? And don't forget, sometimes I'm just writing this way to the side. Maybe you don't want to do that yet. Like, I keep reminding myself, I need to get there. I don't know how to get there yet, but I'm going to make it. So, first, let's get some units working here. Like, I don't want any of these. So, let's do this first. Let's get rid of minutes. So, I'll put minutes here. And how many seconds is that? Well, I can put seconds there, and there's 60 seconds in 1 minute. Well, that just solved two problems right there. Thank you. We're both gone. Okay, now, I need to get rid of coulombs. So this is where, if you just take a breath, you look at your sheet, and you think, how can I get the coulombs? The Faraday's constant is our bridge from current and charge to compound, because it can get us to electrons, which electrons are transferred from ions and species. So I believe on your sheet it says 96,485 coulombs for every 1 mole of electron. Right? I believe that's what it says. I don't have a sheet covered. You're like, well, where do you go next? Well, now get specific. For every mole, how many moles of electrons I have, how many moles of copper? So what's the charge on copper in this one? Is it a 1 plus or a 2 plus? Just look at the sheet. It's a 2 plus. So for every one of these, I have 2 of these. And I know this. Some of us, this is going to be hard to pull through if we didn't have guidance on it. But this is the second or third time I've shown this recently, and I'm hoping that some of it sticks. I hope now we can get there. I'm in moles, right? I need to get the gram. But I hope you understand that I'm just using units. I didn't sit here and go, oh, I know it's 7 steps. I'm good. Like I don't know where I'm going with it. I'm taking my time. I think that's right. And then I calculate it through. But this, to me, this is the important step right here. You have to understand that this moles of electrons then can transition into the atom, the ion, whatever, however you view that. Mine's approximate, because I might be using slightly different Faraday's constant from my math to the problem. So, first, if you did this right here, you got a point. So you may not have needed to do, maybe you didn't do the T-chart at the beginning. Maybe you're like, you know what? My gosh, they gave me amps and they gave me time. You could have done that. You guys, you could have done these two things first. Match up the time, because that's minutes. You did in seconds, time Q, and then you could have started there. Because Q is coulombs, and then divide by coulombs, and then 1 point for the answer. You might recognize that. Have a good practice. I almost made it. 1 more. But the whole thing was worth 2 points. Finally, calculate the dry volume in liters measured at 25 degrees, 1.16 atm of the O2 that is produced. Okay, so this is what I want. I want the volume of the O2 produced. There is a trick to this. I don't know how much O2 I have yet. Think about what you have. Think about how you can get to it. Think about what you don't have. What are you missing in this problem right now to fulfill this? Okay, that might be a clue. So I have 1.19 grams of my copper. I want to know the moles of my oxygen. So that's something that you would need to have done. So whatever answer you have, go with it. You could have a wrong answer here if you didn't have something like 1.19. Commit to something. Go back a little bit. Go back to moles, even though we were in moles for a moment. And then it's a 2 to 1. Should be a small number. You're never going to have a lot of gas. And now I just plug it in. And hopefully that all works out. 1 point for the number of moles of O2. You get 1 point for calculating B consistent with previous calculation.